Welcome. It's our pleasure to have with us Professor Satyanarayanan Chakravarti, who is a professor in the Department of Aerospace Engineering here at IIT Madras. He is basically a BTech from IIT Madras, and he has got a PhD from the Georgia Tech Institute of Technology, Georgia Institute of Technology, also called Georgia Tech, I guess. He's been a faculty in IIT Madras for 20 years. His areas of research are propulsion and combustion. In fact, he's a recognized expert in both these areas. So he's the coordinator for the National Center for Combustion Research and Development, which is housed here in IIT Madras. He's also the coordinator for the Center for Propulsion Technologies. So he has a lot of experience, worked with a lot of students, and so we feel is ideally suited to discuss research aspects associated with aerospace engineering. So welcome to this.
Thanks a lot, Pratap.
So aerospace engineering. So generally, so this is the camera that it will be easier for you to. So if you look at aerospace engineering in general, what would you consider as traditional areas of research in aerospace engineering, which maybe people have been working on for a long time? So there's a lot of literature available in these areas, but still these are areas that continue to be looked at.
Yeah, broadly across the world, in most universities, if you look at a typical aerospace engineering department, there are three broad areas. So the first broadest area is probably aerodynamics, which in many places also includes flight mechanics, but in some places there are specialized faculty research intense in flight mechanics, so they try to treat it a little separately, but normally aerodynamics includes flight mechanics as well. And then the second large area is structures, which also of course includes some materials, smart materials, those kinds of areas, but typically dealing with the shapes in which materials are formed to get aircraft and other spacecraft components. And treating the loads and all those things. And the third one is propulsion, which pertains to engines, the ones that propel the aircraft or the spacecraft. So engines would also include things like rockets and so on. So these are the three broad areas you can say that most of aerospace engineering gets itself slotted into.
Okay. In addition to these, are there certain areas that are considered, modern areas of, or very recently started areas, initiated areas in aerospace engineering?
Yeah, very much, because say for example, as we speak, we are now beginning to see a emergence of, for example, unmanned aerial vehicles, micro air vehicles, and so on. So there is a lot of buzz in the society about these things. So that's an area that requires a lot of specialized attention, and so it is kind of grooming itself into a area by itself. But if you now look at like its aerodynamics, like for example, if you want to mimic insect flight or some such thing, the aerodynamics is horrendously complicated. So that gets to be a specialized area there, and similarly the structures of flapping wings and aeroelasticity is like a specialized area that is coming out to be there. And of course these areas have been applied in the past as well, but they are actually getting more specialized and focused for, let's say, a UAV kind of application. Similarly, micro thrusters for propelling these devices. So in all these traditional areas, you're now beginning to see like deeper focus. Similarly, things like controls for modern aircraft as well as these newer aircraft that we are talking about, space technology going forward into deep space missions and so on. So these are all some sort of newer areas that are emerging.
Okay. And see, if you look at say what industry is interested in, of course aerospace industry is directly interested in much of what you are doing. Are there other industries also which which are maybe peripheral, not directly aerospace industries? Are they also interested in some of the kinds of research activities that go on in aerospace engineering departments?
A lot actually. So in fact, because aerospace is somewhat exotic, so there is a lot of pioneering research that happens in this field. So just to give as an aside, as an example, for example, the personal computer actually started with the space shuttle. Okay, so this was in the 1960s that they were trying to develop, and then so now it is so ubiquitous. So likewise, a lot of things that the automobile people actually adopt, like even things like head-up displays or the driverless cars that we are talking about, have been pioneered in aerospace. So so that way there is a lot of applications that aerospace people can do, like development of new materials, smart structures. These things have a lot of applications. On the engine side, for example, engines go along with not only propulsion but also power. So things like power generation devices, electricity generation can be done with things like gas turbines, which are also the same kind of cycles that are adopted in aircraft propulsion. And there are many such examples that we can give of terrestrial, what we call as terrestrial applications. Okay. Actually,
and in fact, in an associated context, see, typically when we look
wind turbines. I'm sorry, wind turbines is something that is also because of the thrust on renewable energy. Yeah.
Okay, great. In that context, if you look at, say, again, industry expectations of the people that they absorb into the industry. Generally, there is this impression that if you do an MS or a PhD or a specialist, and so there's a little narrower area where you may get absorbed. In that context, where do you see, say, let's say the recently graduating MS PhD students, what sort of positions are they getting, say, in industry or anywhere else? What sort of positions do they end up being?
Okay, so I think this answer I would like to actually take a step back and do a little bit broader outlook.
Sure.
So if somebody is doing research, there are about 3 different facets to it. So one is looking at the phenomena, looking at the process that they are trying to research. The second one is where it is being applied. And the third is what are the skill sets we are acquiring in order to be able to do the research that we are doing on the phenomena that is applied to something. Right. So if you're like a phenomena kind of person, you're probably cut out for academic pursuits. If you're the application kind of person, you probably are looking at what traditionally we call as core jobs. That means, like, okay, obviously when you come to aerospace engineering, it's very unlikely that you will be actually doing sports medicine in aerospace medicine, aerospace engineering, although it is related. Okay, so there is a lot of aerodynamics and structures of muscles and stuff that there are faculty members in some universities that do those things. Okay, so that's an application area. Your core area may be sports medicine or something, but you can always associate a core engineering job associated with the application of what your research is. Outside of that, the larger area is the skill sets thing. So if you're not this phenomena type of person, right, you can now try to leverage the skills that you're learning, right. So the skills typically broadly again fit into 2 or 3 categories: experimental skill sets, computational skill sets, and maybe analytical skill sets. So all these 3 things are there. So for example, we do very advanced laser diagnostics, which can be applied to, let's say, flow past automotive vehicles in trying to making them more streamlined and so on, or do things like FEM or CFD analysis, which are computational tools that are ubiquitously adopted in lots of different applications. So the question is, which one do you want to leverage? What tickles you? What fascinates you? Are you trying to actually unravel physics? Then you probably want to be an independent researcher all the time in your life, and that's one kind of job profile that you will try to attack. If you're a applications kind of person, you will look for core jobs. But if you're trying to leverage your skills, the world is open for a lot of options. Yeah.
Okay, so let me step back a bit. Now we spoke about students who are leaving the program and where they may end up going to. Let's look at the people who come in. I mean, presumably you may have in fact students from different backgrounds coming in,
that's correct.
And also some coming from aerospace engineering itself, from maybe different universities and so on. Yeah. They are also transitioning from course-based education to research-based education when they go for an MS
Absolutely.
or PhD degree.
Yeah.
Are there specific issues that you see them encountering as they settle into this phase of their educational existence? Is there some other any things that the challenges that they face, or and if so, what should be done for them to be prepared?
Yeah, this is again a general question that is not necessarily aerospace specific. Okay, so I'm going to answer it in that way to start with, sure. And see where aerospace fits in if required. But fundamentally, what I see is that right from kindergarten to let's say undergrad, or let's say a course-based masters like an MTech program, each child to start with and ultimately going to being an adult is actually programmed. So we have a timetable that's given at the beginning of the semester or a year, so we know exactly where we need to be sitting, in which room, in which seats, perhaps at which time, and so on. So we are not really trained to think independently on how we want to spend our time. And when you now become a researcher, so if you really think about it, even when you are doing coursework, right, to start with, you're doing like lot less number of courses when compared to a typical MTech or a BTech, and lot less when compared to what you yourself did when you were a BTech or an MTech, right? So you probably did like about 6 courses and a couple of labs that kept you busy pretty much all week with all the homeworks and assignments to boot. But now you probably are doing like about 2 courses. What do you do with the rest of the time? So typically, I think this hurts the master students more when compared to the others, the PhDs, because they have this mindset that I'm doing courses, so let me not do any research. Okay, and that's actually a bad strategy, because they are just wasting a lot of time saying that they're doing research, so courses, and that chunk of time is like an appreciable part of, like, let's say a master's. So a master's is supposed to be like about 2 to 3 years, but typically everybody thinks it's a 3-year thing rather than a 2-year thing, which doesn't have to be actually, right? But they pushed it that way because they had this, taking it easy during courses. I think this we have to inculcate in our students to do a much better time management. They need to understand that there are 24 hours a day, there are 7 days a week, 168 hours a week. The moment you say like there is 168 hours a week to somebody, they don't even know that, because they've not done that little arithmetic, right? And they don't know that how to use those hours. And this is something that I find most students are not really cut out managing very well. They get into some kind of a sudden expansion of a lot of freedom, where they are not being monitored, they are not being required to be in a particular place doing particular thing anymore, and they are on their own doing things, which is very, very hard to sharpen and say, at the end of 1 year, what have you achieved? Maybe a lot less than what you would have if you had been a lot more conscious of your time.
Okay, great. And also in terms of preparation for, let's say, the kind of detail and rigor we have for our coursework here and so on, do you find generally students coming in, are they well prepared enough that once they come through our selection process, they are able to handle all what we require of them here, or do you feel they are maybe, is there any challenge they face, let's say, with respect to the math involved in our courses, any other analytical skills? Are there things that they need to be more aware of?
It's an evolving thing. So one is, maybe they are not really prepared for it, maybe, but maybe they are. So that's a spectrum. But many of them adapt. So okay, when they come in, they know what is expected, and therefore they try to adapt. They try to pitch themselves at a higher plane that is required of them, and so on. Progressively, I'm seeing in the last 20 years that I've been around, our expectations are also getting elevated. So we are, for example, if you see that there are lots of advanced level electives that are being offered with more and more faculty coming in, and with greater levels of specialization and new areas that are being filled in, interdisciplinary courses and so on. So the level of expertise expected of the student is increased, and if you increase your expectation, many times the students rise to the occasion and meet it. Okay. So that the most important thing is to actually keep our expectations at the level that is appropriate, and not necessarily water it down. Of course, don't make it too high as well. That gets a bit unrealistic. But I think it's important to not let down the expectations, and hold it at a certain level, and get the students to rise up to it, and they would do it.
Okay, great.
Yeah.
And okay, maybe a sort of a mundane question related to this kind of the life that students have as their during their research activities here. There is always this idea that a lot of learning happens when they interact with fellow students, with their faculty, with their guide, and so on. What do you feel is a good frequency with which students should be meeting their guide?
Well, I've been on an average doing like once a week or so, and once a week, or maybe sometimes because of travels and conferences and all that stuff, it may be like once in 2 weeks. But I think we need to give some, so if you're particularly talking about guides versus students, that's a different equation when compared to students meeting fellow students. So I think that students meeting fellow students has to be happening all the time. I mean, they must be in the lab, and the lab has to have like a bunch of students working on things. Maybe sometimes one experiment or whatever it is it may not be possible to actually be done by one student, but it doesn't mean that every student gets a helper to help him or something. That doesn't make sense at all. So therefore, like, students will have to actually combine their resources, and they may be also sharing equipment and so on. So like if one person is doing his experiment, the equipment gets tied to that experiment, which means like it is not available for the next student who is sharing their equipment. So that means like they have to have a very good helping tendency, and they are not really helping for nothing. I mean, it's like when I am helping my friend in the lab, he is going to help me when I am doing my experiment. So
it's a learning experience.
So typically what's happening across the world in many places, and you might find this actually, the number of authors is kind of proliferating in many journal publications and there is a reason for this. So many labs are actually getting on a campaign mode. So they now say, okay, now I'm going to actually work on student X's experiment. That means the entire lab works on student X's experiment on a campaign mode. So that means they finish the experiment in about a week, get that student X to actually process all the data, because there is just many times these days we are getting a lot of data, either it is numerical work or experimental work. It's easy to get the data, a lot harder to understand, process, and there is too much post-processing that we need to do to squeeze physics out of it and all that. So let him do the post-processing, but he should be available to actually get into the next campaign during the daytime or something like that with the other student and so on. So then it turns out that many of these people actually get on each other's publications and so on. It's not a bad deal actually, and they learn about each other's experiments, the nuances of the problems that they are working on. So I think that kind of time sharing and time management among students is very important. As far as the guide is concerned, I think once a week, either an individual meeting or at least a group meeting is pretty good, particularly in the Indian setting. I think when compared to, let's say, Germany or somewhere else where students don't meet their guides for a very long time, and still they are on their own because they know how to work with their hands and they know how to craft things and so on, whereas I think our students are not very well prepared to do things. So we have to actually shed our ideas with them, and we don't really have a very extensive postdoc culture. So that means like all the nitty-gritties is something that people get stuck on, and we do end up doing some kind of like repetitive teaching of these little skills. So I think skills development, more than, for example, teaching and interaction, I think skills development of students has to be focused upon. So if there is a way by which we can actually develop a lot of skills, for example, things like if somebody wants to learn Fourier transform, right, he needs to go to some place and learn it. So there could be like some sort of a YouTube video lecture of about an hour with lots of equations, or like, let's say, MATLAB programs and so on that are available in a repository, like an NPTEL thing. So, but it doesn't have to be like a formal course for 50 hours or something, because can I just learn something quickly, right? Those kinds of skill development is something that if we have a very good base of it, the faculty involvement could be a little lesser. But one of the problems that we have in having to have an involvement is we are not really making a lot of progress on what our original research goals are in these frequent interactions that seem to be a must right now, simply because we are actually plodding through developing skills of each and every student all over again every time.
Okay. Yeah. I think that's a very pertinent observation for where we are doing, how we are approaching things today. In terms of, again, one of the things you mentioned, this multiple author publications and so on, and of course, generally we tend to look at publications as one measure of how progress is happening in a research scholar's activities. Is there any other way that you feel, in a more philosophical sense, that you feel you need to look at a student, or a student needs to look at himself or herself to understand that they are actually making progress in research?
This is a very difficult question, and this is sort of highly personal, as in every researcher, and this doesn't have to be necessarily a faculty member, it also pertains to a student researcher. So every researcher has to actually make up his mind what's going to make him sleep well that night, that he has a sense of accomplishment. And of course, as a researcher, sometimes I spend sleepless nights thinking about my research. So, and that doesn't count. Okay, so if I'm doing that, I'm quite excited about my work and so on. That's okay. But I think the sense of accomplishment or achievement is highly personal, and there are lots of ways by which this can be done. We can measure in terms of metrics like number of publications, or the impact factors of the journals, H index, whatever it is that you want to talk about. And you may claim that you're bringing in some quality and citation index and all those things into picture in all that stuff, but I don't know if that's what is going to make you happy, right? So keep in mind in the Indian academic context, okay, I think most of the academics in India are actually on this job because they want to derive satisfaction out of the job that they're doing. And job satisfaction on the whole in most industries is an oxymoron. I mean, you either have a job or you have satisfaction. So it's one of the okay. So
Okay.
so here I think we are trying to do this. Okay, so and we have to actually ask ourselves what satisfies me. So there are people who want to see what they're doing actually be applied in the industry. There are some people who want to actually look the most scholarly. And like, for example, if you look at G.H. Hardy's book, An Apology of a Mathematician, he actually loathes his number theory being applied to, let's say, chess games or something like that. So there are these purists who don't want any application.
Okay. Yeah.
Okay, so you have to respect them for what they are.
Yeah,
Okay,
yeah. They feel you are lowering the
exactly. So you have to respect them for what they are. Yeah.
Okay.
Yeah.
So maybe to close, actually, I just wanted to get your opinion on, or actually your words of advice. What words of advice would you have for students who are aspiring to join an MS or a PhD program in aerospace engineering?
Simple 3-word answer is follow your heart.
Okay.
Okay, so I think this is true for anything. So whatever you want to do, so we have a lot of societal pressure, unfortunately, because we are still a developing country. Okay, so there is like a lot of pulls and pressures, family, blah blah, lots of things. So I think at the end of the day, we need to make up our minds what we want to do, and we have to follow our heart. So if you want to do research and we want to do a particular kind of research, we want to do a particular topic of research, if we want to work with a particular guide in a particular department, a discipline, whatever it is, just do what you think is the right thing. Don't worry about anything else. Everything else will work out for you. I think you can have this attitude like the universe was created for your sake. Okay, just go on, and everybody will follow. Not a problem.
Okay, great. Thank you very much for joining us. It was a pleasure. I think a very nice insight
Thank you very
into
much.
what students should look at.